see, B, item B, intrinsic geometry, exterior algebra in 3 dimensions. Could be any dimension, okay? We are working at 3 dimensions. So B, item B, part 1, lecture 10, direction derivatives. Now, in this lecture, we will talk about the direction derivative involving these functions fi from the previous lecture 9. You see, those are level curves belong to the manifold M3. This is a constant, so these are level curves, okay, belong to the manifold. Now, you see, again, we already discussed, presented in other videos, the curve gamma of lambda, which is x1 of lambda, x2 of lambda, x3 of lambda, where the real lambda, real number, it's a real number, varies between a and b. Now, a is gamma of minus epsilon, p is gamma of 0, and b is gamma of epsilon here. You see in this figure 2 over here. You see? Now, you see relation to and the equation here, and also the level curves, Then we can use directional derivative along the curve gamma of lambda. By composing the level curve with the curve gamma of lambda, this gives, you see, fi of lambda, fi x1, x2, x3 of lambda, which describes how if you move, attention now, if you move here, it's very lambda, you feel, you see, how when you move here, you feel how fi is changing when you move lambda. You see, that's a very interesting and a fundamental concept on calculus, okay, advanced calculus. So I composing, and then I can express, okay, these level curves in terms of the coordinates, okay, of this red curve over here between A and B. Why between A and B? You see, epsilon is a small but finite quantity. So then I can substitute, okay, this region here, but the plane, in this case of R3, this plane is a vector space, as we discussed in previous videos, you see? So this is just easy applied math, you see? This I can now, you see, define the direction derivative. This f sub I, they are level curves, and lambda is a variable over here, you see? That's a real variable. So I just composing, then here apply the chain rule, see? I obtain this expression here. Now I, you see, I is free and J is dummy, okay? So this expression will represent the direction derivative of the level curves f sub I along the curve gamma of lambda at point P. Now, coordinate approximation. The formula for this direction derivative effectively captures the rate of change of the level curve in the direction of the curves in the gamma lambda. Okay? So now I said before here, we can approximate. Then will be the space vector. In the case of M3, three-dimensional manifold, the space vector is called tangent space vector, okay? That's a tangent plane. This is a tangent plane, you see, TP of the manifold. Now, it's a very important point here. This TPM are expressed by the approximated R3. You see, when you use, as I'm insisting, you see, in this important concept, when I use the vector space, the Cartesian coordinates R3 in the vector space, we are approximate points on the manifold to this respective plane or space vector. Why I say a plane? Because I solved a numerical example showing that I have a two-dimensional manifold, okay? And the space vector is a straight line. When you work in the four-dimensional, the space vector is not a plane, you see, just as we see later, okay? So that's it. That's directional derivative, okay? Again, when you have a curve, okay, crossing each level curve. So when you move, it feels, this motion feels how Fi is varying when you cross the points of this curve over here. That's a fundamental concept about direction derivative. See, that's it.